In the previous video we introduced the idea of angular frequency. I want to just explain that a little bit more in this video. To do that though, we're actually going to have a look at circular motion first. Now there is a whole unit 6 on circular motion and gravitation, so a lot of these concepts will be developed further in unit 6, but just to tie into what we're dealing with here, if we consider the circular motion of an object, I'm just going to draw the axes of x and y here. So imagine this is the circular path that an object is travelling on. Hopefully that circle's close enough to being a circle. So if we consider a point here where that point's moving around this way, we'd be interested in the radius of that circular path, and then also the angle as measured from the x-axis being angle theta. Now the rate of change of that angle, so the rate of change of angle theta with respect to time is what we would call angular velocity. And it might seem a little bit confusing, but the symbol that we're going to use there is the same as the symbol for angular frequency, and we'll explain why that is in a second. So it's angular velocity, and the symbol, as I said, is omega, and so we can identify that omega is just the change of the angle theta over time. So there's the calculation that we could use for angular velocity. Note that I'm not highlighting that one. It's not one that's in the data booklet. It's just one that's helpful to keep in the back of your mind. If we consider one full rotation though, so for one full rotation we have that the angle that's covered, the angle theta is going to be equal to 2 pi radians, and the time that's going to take is going to be the period capital T. So we can therefore substitute in and say that omega is equal to 2 pi on t. Now that one is in the data booklet, so the angular velocity is equal to 2 pi over the period. To take that a little bit further and to sort of link back to the idea of how we can use omega for angular frequency, we know that frequency is equal to 1 on the period, so f is equal to 1 on t, as we saw in unit 4. We can then make a substitution, given that we've got this divide by t, we can then say that omega is actually equal to 2 pi f. So we're looking at an angle of 2 pi multiplied by the frequency, so as a result omega, as well as representing angular velocity, omega also represents angular frequency, and helps us to then apply that across to simple harmonic motion, and the measurement for angular frequency is radians per second. So always dealing in radians when we're dealing with angular measurements. Now if we go back to this scenario, I just want to touch on one other aspect here to help explain how we can use circular motion as a representation for simple harmonic motion. If we consider the motion broken up into two parts, so let's imagine that we're going to look only at what happens as this object is moving in the XY direction, so imagine sort of looking end on and just seeing that sort of side to side motion, and then we're also going to consider what happens as it's moving sort of up and down if you were to look at it from this direction. So we can sort of see the horizontal and the vertical motions. What we will identify there is that if we consider the x direction, so in the x direction we have at any time t, we can identify where the what the x coordinate would be. So x is going to be equal to r cos theta. So if you want to go through the trigonometry for that, so the x coordinate is equal to r cos theta. But before we saw that omega was equal to theta on t, so rearranging that we can show that theta is equal to omega t. Likewise, given that we're dealing with x, would say that the radius is going to also be equal to the maximum value for the x coordinate, so r is equal to x naught. So therefore we can substitute in, and we end up back with that equation that we've already seen, x naught cos omega t. And we could do the same sort of thing in the y direction. I won't go through the full explanation of it, but similarly in the y direction we would have that y is equal to y naught sine omega t. Now hopefully you can recognize that both of those equations look similar to the ones that we were dealing with in the previous video. So what we can identify then is that perpendicular components of circular motion can be treated as simple harmonic motion. So in class we'll have a look at some problems and some ideas around angular frequency and angular velocity, and sort of do some calculations and a few activities associated with that.